Okay, welcome back. Today we're going to be talking about sex-linked inheritance and why sometimes males are more likely to have a certain trait or condition. And then we're also going to look at pedigrees, which are family trees that show how traits are passed from one generation to the next. So we're going to start off with sex-linked inheritance. So in sex-linked inheritance, genes are going to be inherited on sex chromosomes, and that's why they are linked to biological sex. And this is opposed to the conditions we've been talking about before, which are autosomal. So remember when we were talking about our chromosomes, we had sex chromosomes, which determine gender, and then we had autosomes, which did everything else. So some conditions are located on the sex chromosomes, and those are going to lead to sex-linked traits, which is going to make one sex or biological sex be more likely to exhibit a certain condition than the other biological sex. So these were first discovered by a scientist named Tom Morgan, and he worked at Columbia University, and he actually found these traits in fruit flies, believe it or not. Eye color and fruit flies was sex-linked, and he noticed, and he did the first work with sex-linked traits on Drosophila, which are little fruit flies. So genes on the X chromosome are typically called sex-linked. And again, we are looking at the X chromosome and not the Y because everyone, no matter your gender, has an X chromosome. So remember, biological males are XY, biological females are XX, and everyone has at least one X. Therefore, the X can have traits other than one that makes someone a male or a female. So X traits on the X chromosome are called X-linked, and they are expressed more often in males than in females. And the reason behind that is because there are very few genes on the X chromosome or on the Y chromosome. The Y chromosome is very tiny. It has only genes that make someone male. And because they have that Y, they only have one X. So because they only have one X, if there's some type of condition, mutation on that X chromosome, they will have that condition. So most people with sex-linked traits or conditions are more likely going to be males. Females can have them, but most likely they're going to be exhibited in males because if a male has a bad copy on his X chromosome, he will exhibit that condition because he has no backup. Whereas a female could have a good X and a bad X, and they're going to exhibit whatever is on the good X. They have a backup, so to speak, so that if one of them has a mutation, they have another chance to get a good copy. Whereas males, they don't have that. They have the one X. If there's something wrong, if there's some mutation there, they're going to exhibit the condition. Therefore, any type of sex-linked trait are going to be more likely to happen in males. Examples of sex-linked traits in humans, male pattern baldness, as well as color blindness. They can happen in females, but it's much more rare because they would need the same mutation, or not the same mutation, but some type of mutation on that gene in both of their chromosomes in order to have it. So to have a colorblind female, each parent would both had to have passed down a colorblindness gene. It just makes it more unlikely, but not impossible. So that's the X chromosome. When we look just at the Y chromosome, there are few genes other than what makes someone a male. I feel like that's not the right slide. Maybe it is. So on the Y chromosome, there are more, or there's only things that make you male. So On the Y chromosome, there aren't any genes other than the ones that determine biological gender. And the Y chromosome is very, very small. It's the smallest chromosome. And so again, it only makes someone male. It turns on the production of the male hormones. And it has many different effects or things that make someone male. And it's called pleiotropy, when you have one gene controlling many things. So it turns on the production of male hormones. Those hormones are going to cause they could lead to more height, increase in muscle, deeper voice, facial hair, all different types of things controlled by just one gene turning on the production of a male hormone. So it does many different things to make someone male. But that is essentially all that there is on the Y chromosome. It's very short. It has some genes that turn on the production of male hormones that lead to someone having the traits of a male. Whereas the X chromosome, because everyone has an X chromosome, it has genes beyond just determining the biological sex of a person. Some of the additional genes include mutations that lead to hemophilia, muscular dystrophy, color blindness, and male pattern baldness. And sex-linked is typically going to mean X-linked because they're going to be the mutations found on the X chromosome. So that is the difference between our X and our Y. So the Y genes only that make someone male turn on the production of male hormones, and that's going to cause all the different changes that make someone male, and that's called pleiotropy because it controls many different things in a person. Whereas the X chromosome is going to be much, much larger. It's going to have genes other than that would make someone female, including one that could cause hemophilia, muscular dystrophy, color blindness, or male pattern baldness. So before we get into doing an actual cross and how to do the cross, we're just going to review one more time. So sex-linked conditions are usually also referred to as X-linked, meaning they are found on the X chromosomes. One thing to keep in mind is that all males get their X from their mother because they got their Y from their father. Their mom doesn't have a Y to give, so they had to get that from their dad. So in sex-linked conditions, things are not passed from father to son. They're passed from mother to son, which is, it's kind of interesting to think about when we're saying they're linked to sex, but moms give it to their sons, not dads. So just keep that in mind, that moms give their X to their son. As far as Y-linked conditions, there are going to be very few genes or traits that are going to lead to those. The ones that there are, very few in number, are passed from father to son on the Y, because this one is going to be from the Y, and females cannot inherit them because they don't have a Y. So we're going to look at an example. So hemophilia is an example of a sex-linked condition. Hemophilia leads to the inability to clot your blood normally. So we're going to go ahead and fill one of these out. So one thing to keep in mind, I think we're going to get back to this stuff in a minute, so I will just leave it here. One thing to keep in mind when we're talking about sex-linked conditions, we need to show X and Y. So whenever you see sex-linked, it means we need to show X and Y. X and Y must be shown because we need to show where the traits are being passed from, as well as the gender of the offspring. So when I represent it here, when I make my key, I need to show X and Y. So hemophilia is recessive. So hemophilia is recessive, meaning it's going to be a small letter, a lowercase letter. And it's an X-linked condition, meaning it's found on the X. So when I make my key, I'm going to have an X. Hemophilia is going to be a small letter. So I'm going to have that H. Now we're either using that notation that we talked about from the last unit. You need to be able to use it for sex-linked. So hemophilia is recessive to normal clotting, meaning that normal blood clotting would be found on the X and it would have a capital H. So this is my key. Normal is X capital H. Hemophilia is X lowercase h. A new term you may see is the word carrier. A carrier is just another word for heterozygous. A person that carries a copy of the trait that they could pass to their kid, but they don't have it. So a carrier is going to be someone who is heterozygous, meaning they could pass the little h to their child, but they don't have the condition because they have a big H. So whenever you see carrier, it just means heterozygous. So our question asks, what are the chances of having a child with hemophilia? So that's our question. What's the chance of having a child with hemophilia if dad is normal and mom is a carrier? So first let's look at dad. Dad is normal. Dad's sex chromosomes are X and Y. Y for guy. He is normal. And if we go back up here, normal means he has a big H. So X, big H. There's nothing on the Y, because remember, these are carried on the X. You're never going to have a letter written on the Y. These are carried on the X, because they're sex X linked. So that's dad. Mom. Mom's sex chromosomes are X, X. So mom's sex chromosomes are XX. And it says mom is a carrier. Carrier means heterozygous, meaning mom has a big H and a little h. And that's how we would set up our problem. Now we're just going to have to go ahead and fill in the boxes. So again, it's just like a multiplication table. You're filling it in by carrying them over. Remember, it is very important that we keep writing the sex chromosomes. It's going to tell us the sex of the offspring. Now, when we're reading this one, it's a little bit different because we're not just looking at the traits that the organism has, we're looking at the trait and their gender. Because our averages are going to be different for male children and female children. So, and you got to read very carefully because I'll show you how this could sometimes be misinterpreted if you're not reading quite carefully enough in some of the problems that we're doing. So if we look at just normal versus hemophilia. So let's say, what's the chance of having a normal female? The chance of having a normal female, I would disregard this side. The chance of having a normal female out of all four is going to be, all females are normal. So of the females, 100% are normal. So we're looking at just the females. 100% are normal. Now, if we're looking at just the males, how many of the males are going to be normal? And how many of the males are going to have hemophilia? Of the males, there's only 2 males. All of the males are going to either be normal or have hemophilia. There's only 2 of them, meaning we have 1 here that's normal. That means 50% of the males are normal. 50% of the males have hemophilia. Now you have to read this very carefully, because if I was to say, what is the overall chance of having a child with the condition? Which is our question. I broke it down by males and females here. But what is the overall chance of having a child, any gender, male or female? What's the chance of overall having a child with hemophilia? And it's only going to be this one here. So overall, there's a 25% chance of hemophilia. Sometimes your question is going to ask for overall. Sometimes it's going to ask for including the gender. So make sure you read very carefully, and if your question is asking for overall or by gender, because sometimes it's confusing when I say the chance of having a normal female is 100%, because you're going to look and you're going to be like, well, this offspring right here is not normal. And I'm going to say no, because these are the only females. These 2 on this side are males. These are females. Or the other way around. Sometimes I'll say there's a 50% chance of having a normal male. And you'll be like, normal male is actually 25. It's only 1 square. And again, you have to consider there are only 2 males. So just make sure you're reading carefully. All right, so now we're going to move into discussing pedigrees. So pedigrees are family trees, pretty much family trees, that are going to show how a condition is passed through generations. So a pedigree is a family tree that shows the history of a trait and how it is inherited over many generations. And there's going to be some notations that you'll need to be aware of when we are reading a pedigree. They're listed here, right here in your notes. When we are looking at a pedigree or family tree, and here's some images here on this side that we can look at. Anytime you see a square, it represents a male, so males are squares. Circles represent females, so females are circles. Anytime you see one shaded in, it means that they have the condition. So if this one over here, it says it's looking at widow's peak, if it's shaded in, it means that they have a widow's peak. They have whatever trait or condition you're looking at. Whenever you see a circle and a square attached with a solid line, it means that they mated or that they're married. And when you see branches coming down from a circle and a square, it means that they had children. So these 2, this one and this one, are the children of these 2 parents. So they're connected to their parents via a branch down line. Anytime you see 2 offspring connected in like a little triangle, it means they are identical twins. But if they do not have the line that makes it a full triangle at the bottom, it means that they are not identical twins. So those are rare. You rarely see those unless it's a very large pedigree. And some other times, you'll see a circle or a square that's half shaded in. A half shaded in means carrier. And remember, carrier means heterozygous. So again, those aren't always even listed. Sometimes they're not, the pedigree doesn't have that, so the person could be a carrier, but it's not half shaded. But sometimes the pedigrees do show that. So just in case, that's only a sometimes it will not be. Now, when we're looking at pedigrees, we have to figure out what type of trait is being shown. So when we look at a pedigree, we can tell if a trait is inherited by dominant inheritance or recessive inheritance, and we can also figure out if it's sex-linked. So I will tell you my little breakdown of my steps when I get down here. But for now, we're going to go ahead and fill these out and say what each type of inheritance looks like. So autosomal disorders tend to be found in equal numbers of males and females. Typically the ones that we're going to look at in class, they're going to be pretty roughly equal, more or less. And there are going to be two types of autosomal disorders that we look at. We're going to have autosomal dominant and autosomal recessive. And autosomal dominant, I totally spelled that wrong. An autosomal dominant condition means that every person that has the condition has to have a parent with the condition. So every individual with the condition has a parent with the condition. Versus autosomal recessive means both parents can be normal and have a child with the condition. So if you see recessive would mean if I have both parents not shaded, but they have a child that is shaded. That would mean it's recessive. If I see this anywhere in the whole pedigree, it means it's recessive. And then the last thing would be if it's sex-linked, it means that there's a vastly different number of males shaded in than there are females. And typically in the ones that we look at, it's not going to be a question. It's not going to be a one where you look like, is that roughly equal or is it not? It's going to be, wow, yeah, there's like tons of dudes there and no females. So it's going to be pretty obvious in the ones that we look at if it's sex-linked. So we're going to work through these with some examples, and we're going to start with an autosomal dominant. So whenever I am looking at a pedigree, I follow a few basic steps. I'll just write them here. My basic steps that I look at when I'm trying to figure out, let me see if there's practice at the end. If there's a practice, that would be a good place to do it. Nope. So the first thing that I always do is my first step is it autosomal or sex-linked? So that's the first thing that I have to figure out. The way that I figure it out is by looking at number of shaded males. So I look here and I see there's 2 shaded males and there's 2 shaded females. Pretty much that's equal. So it's not sex-linked. This one is autosomal. So I know that this one is autosomal because there's the same number of males shaded as females. So that's step 1. If it's sex-linked, you're done. If it is autosomal, you still have step 2. So if autosomal, is it dominant or recessive? The way that I figure that out is, does every shaded person have a shaded parent? If the answer to that is yes, then it's dominant. If not, it's recessive. So does every shaded person have a shaded parent? Shaded, parent is shaded. This one has a parent that's shaded. So this one is dominant. So this one, I know it already said it on there, it told it to you. But if not, I could have looked at it and figured it out and said, well, they are autosomal dominant. Now, if the condition is dominant, that means it's represented with a capital letter. I'm going to use the letter A because that's what I like. So it means that every shaded person has a capital. So if it's autosomal dominant, it means that every shaded person has a capital. And if they don't have the condition, then they have to be little because they are recessive. And then I can work backwards to figure out the second letter of my individuals. So this individual here, individual number 8, I know they have to have a little a because it had to come from this parent. This parent can only give a little a, so they had to give that to their child here. Individual number 4, I know that they also have a little a because they had to pass in a little a to their kid here, number 7. Because remember, each child gets one letter from mom, one letter from dad. This parent gave a little a, but this kid has 2 little a's, meaning the other parent gave a little a too. And based on individual number 5, who is not shaded in, they have little a, I know that both parents up top had to have little a's to give, so I can figure out their genotypes as well. So again, if it is autosomal dominant, when I figured it out, we looked at it, we figured it out that it's dominant, that tells me that every shaded person has to have a capital letter. All the people that aren't shaded, therefore, have 2 small letters, and I can work backwards to figure the rest out. Okay, so our next one, I'm not even going to show on my screen what this one is, and we're going to figure it out. So step number 1. Step number 1 was to figure out if it's sex-linked or if it's autosomal. So I'm looking at this here. 2 males, 1 female shaded. That's roughly equal. I mean, it's not always going to be perfectly equal, but it's roughly equal. So this one is going to be autosomal. Remember, sex-linked would be if it was all males, shaded. Now, my second question is going to be, is this dominant or recessive? Now, dominant means that every shaded person has a shaded parent. So here's one shaded individual right here. But their parents are not shaded, so this is recessive. Now, I must tell you, this is a small pedigree, so it's really easy to tell here. If this was a much larger pedigree, you'd have to look at every single shaded person to be sure. Because sometimes a recessive condition, there is a shaded parent. But you know for sure if you look at the whole thing and there's not a single one. So you have to look at the whole thing before you can make your determination. Since this one's small, it's kind of easy to figure out, but on a large one, you gotta look at everything. All right, so we know that this condition is recessive, meaning that if a person has the condition and the condition is recessive, they have to have 2 little letters because the condition is recessive. Meaning that being normal is dominant. Everybody that's not shaded has a capital letter. So if that works easier for you, we can also make a key when we do these. We could say that the condition is, so normal versus condition, whatever it is. Normal, it says the condition is recessive, meaning the condition is little a and normal would be big A. So we can make a key. We could have made a key up here when we said autosomal dominant. That would be telling us that the condition was big A and normal was little a. So if you want to make a key, go ahead, make a key if it makes it easier for you. So down here, this is recessive. The condition is little a, being normal is big A. So we're going to try to figure out if we can get all the genotypes here. So I usually like to, for this one, let's start at the top. So, it's hard to figure these all out. We can figure out these parents, though. So here we know that both of these parents had to have little a's because they gave little a's to their kids down here. Now, all these other ones, there's no way to figure them out for sure. This one here, oh, I lied. This one we can figure out because this parent had 2 little a's and they had to give 1 little a to their child there. So you can figure out that one. But other than that, there's no knowing for sure for these other 2. Sometimes you can't know for 100% sure. There's no parent or child here to tell us anything more for these 3. So we can end with that one. All right, so here's our next one. Our steps again, we start with step number 1. Step number 1 says figuring out if it's sex-linked or autosomal or sex-linked. My question is, are there many more males shaded than females? In this case, we only have males shaded. There's no females shaded, meaning that this one is sex-linked. And if it's sex-linked, that answers our question. We have no step 2 if it's sex-linked. Now, remember with sex-linked, we have to go through and figure out the sex chromosomes. And when we're looking at sex-linked, we're always going to be looking at recessive. Typically, unless it's stated otherwise, sex-linked is recessive. So that would mean that normal would be X big A, and the condition would be X with a little a. So let's go through this square. Number 1, that's a male, so they have an X and a Y. They are normal, not shaded, meaning they have a big A. This individual is a circle, so it's a female with 2 X's. She is normal, meaning we know she has at least 1 big A. We're not sure about the other one quite yet. We'll see if we can figure that one out. We'll come back to it. So going through this one right here, that's a female because it's a circle. We know she has 2 X's. She's not shaded, so she has a big A. This individual here is a male, so they have an X and a Y. They are shaded, therefore we know that they have a little a. Now, remember back when we talked earlier about sex-linked conditions, we said that males get their X from their mom, meaning this little a had to come from this mom. So we can work backwards to figure out that she has a little a. All right, this child here, male, so again an X and a Y, shaded so he has a little a. This individual here is a female, so 2 X's, not shaded, so we know she has a big A. This male is a male, so an X and a Y. He's normal, so he has a big A. This female has 2 X's, and she's normal, so she has a big A. Here's another normal female with a big A. Here, we know that this dad only has 1 X to give his daughter, so this daughter here has to have a little a. Here we have a male, normal. Here's a female. She is normal. Again, dad only had a little a on his X, so she had to get this one. Same with the other daughter. And our last one, you know that it's a female that is normal. And that's all we can figure out. We did the other letters that we could figure out as we went, but that's all we know for now for this one. So there's going to be some practice on sex-linked and pedigrees on Canvas. So go ahead and check